You know, there's a fundamental law of physics hiding in plain sight, something we use every single day without even thinking about it. It's at play when you open a jar, when a huge crane lifts a steel beam. It's the secret of the turning force. And today, we're going to pull back the curtain and see exactly how it works. So let's start with a really simple question. Think about pretty much every door you've ever used. Why is the handle way over on one side, as far from the hinges as possible? I mean, why not put it in the middle, or right next to the hinge? It seems like a tiny detail, but it's actually the perfect key to unlocking this whole idea. The answer is actually pretty elegant. When you place that handle far from the hinges, which is the pivot point for the door, you make it way easier to open. It's not about brute strength, it's about being smart. It's about maximizing what physicists call the turning effect. You're basically getting the most turn for every bit of push. Now, this turning effect isn't just a casual phrase. It has a real, official name in the world of physics. It's called a moment. And no, we're not talking about a moment in time, but a moment of force. So let's dive in and meet the moment. So what is a moment? Well, it's just the measurement of how good a force is at making something spin around a pivot point. The bigger the moment, the bigger the turning power. Really, it's the scientific word for leverage, that awesome turning power we're using all the time without even realizing it. And once you start looking for it, you see it absolutely everywhere. Using a wrench to turn a stubborn nut, you're creating a moment. A seesaw at the park, that's just a fun game of balancing moments. Popping a bottle cap, steering a car, it's all about applying this turning force. It's one of the greatest hits of physics. Okay, so if it's so important, how do we actually calculate this turning power? Well, the good news is, it's not some crazy complicated formula. Honestly, it's better to think of it like a simple recipe, and it only has two key ingredients.
Yup, just two things. That's all it takes. Once you know what these two ingredients are and how they work together, you can figure out the turning power of pretty much any force. So, let's break them down.
All right, ingredient number one is the force. That's the actual push or pull you're applying, which we measure in newtons. Ingredient number two is the perpendicular distance from the pivot. Now that word perpendicular is super important. It's kind of the secret sauce. It means the distance measured at a perfect right angle from that pivot. You have to push at that perfect 90-degree angle to get the maximum turning power. And the recipe itself? You just multiply them. Moment is simply the force you apply times that perpendicular distance. So if you want a really big moment, you can either use a really big force, or you can apply a smaller force at a really big distance. And that right there is why the door handle is so far from the hinges. Let's just put some numbers to it. Say you push on a long wrench with a force of 50 newtons, and you're pushing at a spot that's 0.8 meters from the nut you're turning. You just multiply 50 by 0.8, and you get 40. We call the unit Newton meters, or NM for short. See? Simple as that. You just calculated a moment. Okay, so we get how to create a turn, but what about the opposite? What if you want to stop something from turning? How do you get perfect, stable balance? Well, that brings us to one of the most important rules in all of this, the principle of moments. This right here is the golden rule. It's the absolute heart of what makes things balanced. It says that for anything to be totally still, all the turning forces trying to spin it one way have to be perfectly canceled out by all the turning forces trying to spin it the other way. Just think of a clock face. You've got forces trying to turn something clockwise and other forces trying to turn it anti-clockwise. For perfect balance, the grand total of all the clockwise moments has to be exactly the same as the grand total of all the anti-clockwise ones. It's like a cosmic tug of war, and perfect balance is when it's a perfect tie. Let's look at a classic seesaw. Check out the left side. We have a 20 Newton force that's 2 meters away from the middle. So 20 times 2 gives us an anti-clockwise moment of 40 Newton meters. Now, look at the right. The force is much bigger, 40 newtons, but it's closer to the pivot, only 1 meter away. So 40 times 1 gives us a clockwise moment of, you guessed it, 40 Newton meters. The moments are equal, and that beam is perfectly balanced. This whole idea of perfect balance leads us to a really big final concept. It's the state that every engineer hopes to achieve when they design a bridge or a skyscraper. It's called equilibrium. So equilibrium is just the state of total absolute stability. It means there's no overall force pushing or pulling the object in any direction, and there's no overall moment trying to spin it. Everything is perfectly balanced. The object is not going to move, it's not going to spin, it's just still. So to get to this state of perfect stability, it really just comes down to a two-point checklist. First, are the forces balanced? All the ups have to cancel out all the downs. Second, are the moments balanced? All the clockwise turns have to cancel out all the anti-clockwise turns. If the answer to both is yes, then congratulations, you've found equilibrium. So really, that simple door handle is your gateway to understanding the physics of balance that literally holds our entire world together. Now that you know the secret of the turning force, where are you going to see it next? A hanging mobile? A giant construction crane? A simple pair of scissors? The world is just full of these amazing balancing acts, and now you know exactly how to spot them.